Hi everyone, I'm Alvina and I'm a PhD student from UCL. I apologize in advance for two things. First of all, I'm a theorist, so I have a lot of equations, but in this talk I've reduced it to only 3. And then secondly, my work has nothing much to do with submillimeter polarization, which is what everyone's been talking about these 2 days, but I'll talk a bit about radio polarization today. The work I'm presenting is done mainly with my collaborators here, so Kinwa and Lydia are my research supervisors, and I'll show some snapshots of cluster simulations from a code by Daisuke and David, and some polarized radiative transfer calculations that I've been working on closely with Jennifer, Jason, Tom, and Curtis. Oh, and I'll be talking about diagnosing magnetic fields in galaxy clusters and large-scale structures today. So what's the current situation right now? The current situation is that we don't know much about cosmic magnetic fields. So there are 3 big science questions that we try to address, or the community try to address. First of all, what generates these large-scale magnetic fields in space, and where do they come from? Secondly, since these magnetic fields are invisible to the eye, so how do we see them? And how do we diagnose these fields to obtain more information about the properties, such as the structure, the correlation length, and the magnetic field strength. And lastly, what is this magnetic field evolutionary history? So how do we know more about their evolution, and what role does the evolving universe play in the large-scale magnetic fields? So to find some answers to these questions, my main research work involves investigating the properties of large-scale magnetic fields and their signatures in X-ray and radio observations. To do that, I assess rotation measure fluctuation methods, I run cosmological MHD simulation codes, and I carry out polarized radiative transfer calculations. These works are important because soon enough we will have the square kilometer array, the SKA, and which will start early science observations sometime middle of next year, I think, with a partial array, and by the time it is completed, it will be the world's largest radio telescope, with a goal to carry out what they call an all-sky rotation measure survey, in which after a year of observing the sky, of observing the Faraday rotation measures for compact polarized extragalactic sources, we will get an increase by 5 orders of magnitude of what current data sets have. So here, the picture here, I stole it from the internet, from the SKA webpage, I've cited it. And what you see here is 1,200 rotation measures that have been compiled. And the blue dots are 900 extragalactic sources, and the red ones are pulsars. So the closed circles are positive rotation measures, so they show magnetic fields pointing towards us as the observer, and the open ones are negative rotation measures. By the time SKA is completed, it will produce an all-sky grid that has an excess of 10 million rotation measures. So it will be a much more dense RM grid than what you see here, and with sources of spacing of like 20 to 30 arc seconds between each sources. And many of these sources will actually have redshift information from surveys such as SDSS. So the RM grid will be a powerful probe to study large-scale magnetic fields and foreground magnetic fields for all redshifts. As such, my talk today, I will begin with a brief picture of cosmic magnetism and why large-scale fields are important stuff to look at. Secondly, I will highlight some results from our in-house cosmological MHD simulations, where I carried out point-by-point correlation of X-rays and rotation measure in clusters. And lastly, I'll talk about how we diagnose these large-scale fields using rotation measure fluctuation analysis and polarized radiative transfer calculations. Right, so magnetic fields are everywhere, and they're present at all scales in the universe. They exist in stars, in galaxies, in clusters, in the IGM, ICM, and even in larger structures such as filaments and voids. So it is largely accepted that the observed magnetic fields in galaxies and clusters are produced and maintained by what we call a dynamo mechanism. But for a dynamo to work, you need to have a seed field, you need to have a field to begin with, a non-zero initial magnetic field, so which gets amplified as structure forms. Now the interesting question here is that where does this seed field come from? Did it exist at the very early universe, so we call that a cosmological origin, or did it come from the formation of the first stars and galaxies during the epoch of reionization? So this is the region I'm interested in. So how can we make magnetic fields? As a theorist, we run simulations. So here I show one cluster from the GCMHD cluster simulation, and we use it to simulate clusters and trace the evolution of magnetic fields through the induction equation. So we plant a seed field of 10 to the minus 11 Gauss and just let it evolve as our cluster forms. So what we find is that our implementation can follow accurately the formation of structures, but the choice of the numerical scheme and the divergence cleaning scheme is actually very important. It has an impact on how the magnetic field evolves during structure formation. So here I'm showing you how we examine the choice of our numerical scheme during the development of the magnetic field itself. On the left you see density slice through the center of the simulated galaxy cluster, and if you look at all 6 panels, they look the same. But if you look on the panels on the right for the magnetic field strength, they look completely different, even though they're the same cluster. So what has happened here? So each panel is numbered according to the choice of our resistivity scheme and our choice of divergence cleaning scheme as well. So by eye, we said that, okay, fine, the density all looks the same, but for the magnetic field, the choice of the numerical scheme affects, first of all, the strength of it, because the colors here shows the different strength of the magnetic field, with red being the highest. So there's this red bit here. So what's that actually? It's actually what happens in the first panel is that it's a control test, so there's no resistivity, there's no divergence cleaning, and the red blobs is actually the divergence, so it's an artifact because the magnetic fields are not divergence free, so it's actually not real. The rest of the panels have a lower magnetic field strength because you don't see any red blobs in there. And the most ridiculous one is in panel 4. My magnetic field has completely disappeared. What happened is because the numerical scheme has been applied too much that the whole magnetic field has disappeared. Because what the magnetic field strength that we're looking at are really weak. We're looking at about microgauss and lower. So what I'm trying to show here is that we have to be very careful with applying the numerical resistivity scheme, and for the weak field regime, perhaps only divergence free scheme is sufficient to actually show, to actually trace the magnetic field as it evolves in our simulations.
So what does TP13 mean?
Oh, TP13, so PN05. So this is no resistivity, and this is a control, and then these are the numerical schemes following Price and Monaghan. So there are papers who did the authors who did the resistivity scheme, yeah, and TP as well. So 2 different resistivity schemes here.
Okay.
Yeah, and these are like with cleaning and with cleaning and no cleaning of the divergence free filter. So there are 2 things. This is artificial resistivity, and this is divergence cleaning. So the traditional way is people use resistivity schemes to control the evolution of the magnetic fields, and it's a good way, it's a good approach when it's like when we look at strong magnetic field regimes. But when we look at clusters and beyond, where the field strength are really weak, we have to be really careful with how much we apply the resistivity. And we find that if we look at clusters which have such weak fields, as long as you control your cleaning properly, you don't actually have to touch that artificial resistivity. It's enough to just clean it properly. So part of my research work is that, well, we produce all these pretty pictures from our simulations, but what's the point if we cannot compare with observations? So observationally, about 20 to 30% of massive X-ray luminous clusters are found to host what we call diffuse diffuse megaparsec scale radio halos with low surface brightness. So we're looking at several microjanskis per arcsecond squared at 1.4 gigahertz. So a fraction of these clusters, for example, the one I have here, A2219, you can see that the color image is actually the X-ray emission from ROSA, and the contours are the 20 cm radio emission from the VLA. And what's obvious here is that the radio contours lie on top of the X-ray as if they know each other. But why should they when the X-ray is from a thermal process and the radio is from a non-thermal process? So this is a question that has been in debate for a while. Aside from that, people have tried hard to quantify this. One of the methods they use is to correlate the radio surface brightness on the vertical axis and the X-ray counts. And what they find is that there seems to be some correlation between the two, and the thermal and the non-thermal electrons appear to know each other. And we don't know why. So the question I ask is, does the power law relation also arise from cluster simulations? And we find that yes, it is possible to reproduce results consistent with observations. And here's a cluster I took from the MHD simulations at current redshift. And on the left, I plotted the synthetic X-ray in color, and the white contours are from radio. And what I find on the right panel is a positive correlation between the two. I did two linear fits, one with getting rid of the center, so there's a bit of a tilt here. So with the red bit, so if I ignore the center of the cluster, I get closer to 1. Because sometimes with the center of the cluster with MHD simulations, you get this anomalous over dense region because of one of the disadvantages of using MHD simulations. So some people tend to actually ignore the center of the clusters when they do correlations. Okay, I'm almost done. What else do I want to say? Oh, I'm having the same problem like Anna. I forgot what I wanted to say after the bell. Okay, I'll just finish 2 lines. So the questions we ask is that are the non-thermal electrons from the same population as the thermal electrons? Could be possible. I mean, like they could be an acceleration mechanism that accelerate these thermal electrons to high energies to produce radio emission. So from the slope, it is possible to distinguish a possible acceleration mechanism if we use more sophisticated techniques in our simulations. For example, if we introduce, say, AGN feedback or cooling, then maybe we will be able to come up with better conclusions on the origin of these radio halos. Because I've run out of time, so I'll leave you with a summary here. That's all. Thank you. Any questions or comments?
So when you have this incredible rotation measure grid, it just seems just amazing. There will be some direct observational tests that you envision, which could help us choose, whether they're cosmological seeds or whether it's star formation. That would
potentially.
That would be. I mean, it's impressive that you could tell the difference. I mean, you're looking at rotation measures that are happening at very high redshifts or something.
Yes. Yeah. So be able to trace. Let me go back to that. Yes, so it would be like all sky grid of rotation measures of like 20 to 30 arc seconds between the sources. It would be super dense, and we're looking at 70 megahertz to 10 gigahertz sort of bandwidth surveys, and yeah, and you will be able to like detect possibly very weak magnetic field of the cosmic web. Could be possible. I mean, one of the science goals, may be able to see the evolution of magnetic fields in galaxies and clusters, and possibly the structure of magnetized plasma along the line of sight and across the sky plane. So these are some of the possibilities coming up. Next generation SKA.
Because there are several cosmological simulations that successfully reproduce the largest scale structure of the universe, but did not take into account cosmic magnetic field.
Sure.
So I wonder whether can you quantify the impacts of these cosmic magnetic fields, the formation of large scale structure? Can you comment?
So are you asking me whether magnetic fields are important?
Yeah, how significant? Yeah.
It is very significant to me because my PhD thesis depends on it. So yes, well, if you look at even for clusters with and without magnetic fields, we're looking at just microgauss, and in terms of the, how do I call this, like the yeah, because I guess when you look at magnetic fields which are stronger, obviously they affect the structure formation. When you look at weak ones, we'll be able to distinguish between the origin of these magnetic fields, whether they're cosmological, whether they're astrophysical, whether the first stars made them, or they just appeared out of nowhere at the very beginning. So this is why we want to probe into such large scales, because voids and filaments are pretty much more undisturbed compared to clusters. With clusters, we cannot know the origin because they're so much has happened, they could have merged, and we lost the information from the very beginning. So what we see now is the end product. But if we look into voids and filaments, we will be able to tell what actually happened in the past and give us some hints on the possible origin. So my short answer is yes, magnetic fields are important.
Are there any other questions? Let's thank the speaker.